Hi, everyone. Thank you for joining us, and Happy New Year. Today, we're going to be talking about understanding burner retrofits and control upgrades for efficiency improvement. This is a technical presentation regarding burner and burner control retrofits for steam and hot water boilers to improve operational efficiency. As Ashley said, my name is Chase Bean. I'm the Director of Engineering and Business Development. There is my email there. If you have any questions, feel free to reach out to me. For an overview, today we're going to be looking at the importance of combustion efficiency, innovations in burner technology and controls, considerations for retrofitting, selecting the right burner for your application, utility incentives, and then a cost and benefits analysis. And then we'll finish up with some Q&A. There's also some Q&A slides along the way. We'll also have some polls launched during the presentation, so keep an eye out for those. Importance of combustion efficiency. So I think people are familiar with boiler efficiency, but when you talk about combustion efficiency, we're talking about attaining complete or on-point combustion with as little air as possible. So achieving combustion efficiency helps you achieve your boiler efficiency, your maximum boiler efficiency. There's two conditions here that outside of the ideal operating point. That's the first is when airflow is too low, so that's called air lean or fuel rich. In that case, you get unburned combustibles and incomplete combustion products like carbon monoxide, and those escape the furnace, and which is lost heat. And additionally, you'll get soot buildup in the furnace, which will insulate the furnace walls and tube surfaces, reducing your heat transfer. The second condition is airflow is too high, which is air rich or fuel lean, and the extra flue gases that result will decrease the boiler efficiency and heat is lost up to stack. So basically, you're just having way too much airflow, which represents this mass that has to be heated, and so energy is wasted going into heating that air, and then that air is lost up to stack instead of being transferred to your boiler water. For natural gas, 15% excess air is typical for ideal combustion, or on-point combustion, I should say. Now we'll talk about stoichiometric combustion. So stoichiometric combustion is the concept of ideal combustion, which in practice is actually unattainable. So since natural gas is mostly comprised of methane, we're going to look at the combustion formula for methane. Combustion, the reaction of combustion is also called oxidation. So this is this first equation here is methane in air. It's kind of a simplified version. Like I said, in reality, natural gas has other constituents, but methane with the main components of air, which is oxygen and nitrogen, results in carbon dioxide, water, and your leftover nitrogen. The nitrogen is not even really part of the reaction, but it's there to represent the mass flow of the air. Excess air is actually required to complete or to ensure complete combustion. And when you say complete combustion, you're talking about where practically all of the fuel components are combusted. So methane combustion with 25% excess air is given by this formula. So you have your methane, you have the 1.25 multiplier on the air, and the difference here on the products is you actually have this O2 constituent in your flue gas and more nitrogen here. So this oxygen is what is measured when you're looking at a flue gas analyzer. When you talk about O2 percentage, that's what we're talking about, the extra oxygen that wasn't burned in the combustion process. Poor efficiency indicators, so high stack temperatures. If you are analyzing the flue gas higher than expected O2 levels, flame rollout, which is indicated by discoloration on the outside of the boiler. Fuel smell. Oh, there's a poll there. We're kind of talking about these items, so go ahead and participate in that if you would like to. And then the last item is boiler set point is not maintained at high loads. So if you have soot buildup in your boiler, then you're not getting your heat transfer you want. So that's an indicator that you're getting poor combustion. So if you're not able to hit set point at your maximum capacity of your boiler, even without the soot buildup, though, just poor combustion efficiency is going to result in lower heat transfer to the water. Retrofit savings potential is increased for larger boilers. There's more energy. We're dealing with more energy, so more opportunity for savings. No NOx concerns. So sometimes if you have NOx limits, those are handled by you actually reduce NOx by using more excess air, which when we're talking about efficiency here, we're talking about reducing the excess air to an ideal point. If they're using excess air to control the NOx, you can't turn it down. Otherwise, you're no longer hitting your NOx levels. So that can complicate things. High fuel costs are always result in higher savings with efficiency measures. High operating hours, same thing. Varying load, that's important. We'll talk about that later, but a lot of this efficiency improvement comes from partial loads. And then frequent maintenance issues. That's just an indicator that your burner's just not performing like it should. And if you're having maintenance issues, you're probably also having poor efficiency. Impacts of poor efficiency. So the main thing, obviously, is increased fuel requirements, which is also tied to poor boiler efficiency. And increased fuel means increased fuel costs, but also higher maintenance costs and things, so higher operating costs. Poor emissions, black smoke coming out and of your stack, that type of thing, and as well as increased carbon emissions just due to poor efficiency. Reduced boiler lifespan, increased maintenance costs, and safety concerns. So you could have carbon monoxide release due to poor combustion. You can have sooting in your boiler, which leads to premature, at least the hot spots in the boiler, which leads to premature failures. And those can always cause a safety concern. And premature boiler failure, yeah. Any questions on that section? Are we having any questions?
No questions yet, but if you guys have any questions, you can just leave them in the chat.
Okay, great. The next section, we'll talk about innovations in burner technology. So this is kind of just a timeline of boiler development, starting in 17th, 18th century with just open flame boilers, moving into multi-tubular boilers in 19th century. Then you start getting mechanical drafts, oil burners are developed, gas burners mid 20th century. Then you start getting into real advancements in combustion control and low NOx technologies, and now it's continuing to evolve as the integration of digital controls. Here I have a chart of kind of an efficiency hierarchy, if you will. So you have a single stage or an on-off burner, multi-stage, modulating, parallel positioning with VFD, and full O2 trim system is kind of your highest efficiency. And we'll go through some of those. We're going to skip single stage. That's basically just a burner that comes on when there's a call for heat and turns off when there's not. I had a question that, can we share the recording? Yes, the recording will be available after the presentation, and we'll tell you about that at the end where you can find that. Thanks, Don. So talking about each of these, first is multi-stage burner. So this is when you talk about multi-stage, this is where you have staged firing rates. So instead of a continuously modulating firing rate, there's set firing rates. Some common versions of this are the low high off burners. I don't know if you could consider that an on-off burner because the low fire is really just used for ignition, and then once flame is established, it moves up to high fire and it stays there until the burner turns off. Another common one is low, high, low. And in that one, you actually, you light off in low fire, then you modulate to high fire. When the set point is reached, you modulate down to low fire, and it will toggle between as necessary. And until it's just still overfiring at low fire, and then it'll cycle off. But that's kind of the idea. There's also burners that have different stages in between as well. But these are kind of the two common ones that you'll see in commercial boiler rooms. So modulating linkage. So this is really kind of the target that we're talking about for this presentation. A lot of the retrofits are going to come here. Any of the lower technologies on that chart are, they apply for retrofit, but this is the common one that you're going to be looking at. So this is also called single point positioning or jack shaft controls. You'll see that sometimes, but basically you have a linkage here. And so you start with an actuator. This is why it's called single point position. This is the actuator for the gas valve, the damper, and the fuel valve. So this actuator is hooked to a linkage that goes across. As this bar turns, it turns the the linkages push open the gas valve, the air damper, and the secondary fuel, in this case fuel oil valve, all from one actuator. So these are all controlled just based on ratios in the linkages. It's kind of an art to get them tuned in right to where they're firing right across all ranges, and then due to the nature of these linkages operating, they get loose over time, maybe get bumped and get out of tune. And so they have to be tuned periodically, where a technician will come in and adjust the linkages, tighten things up, and try to achieve optimal combustion across the firing range. For this type of controls, this is a modulating control, so there is like a continuous, like you can hit all the operating points between low fire and high fire, not in stages, but continuously modulating. But it is a mechanical modulation, so it's like you can't set up your efficiency points to be ideal for all or across the whole firing range. It's going to be really ideal at some points, and then you're going to have to kind of have some excess air at other points so that you don't get a fuel-rich condition. So it's not finely tuned across the entire firing range is the point. For dual fuel as well, the setup will favor the efficiency of the primary fuel. They will try to get it tuned in as well as possible, but there's really an art to it, and there's a lot of room for error. And it's really, you can only get it so far. You can only get it so tuned in, if you will. So it also does not account for changes in ambient temperature. Nothing's being measured here and adjusted for. It's set it and then leave it and let it run. So it's not accounting for changes in ambient temperature, and it's not accounting for changes in fuel quality. The next technology here is parallel positioning. So with this, instead of having that common jack shaft, we're having an actuator here on the air damper, as well as an actuator on the fuel valve. There's also an actuator on secondary fuel that's not shown. And these are adjusted based on a pre-programmed curve. And so control is more precise, less excess air is required on average across the firing range. And the control curve can be customized to optimize combustion across the entire firing range. The burner still has to be inspected quarterly, but adjustments are typically minimal. There's no linkage, so the boiler does not easily get out of tune. For dual fuel burners, you can switch modes between fuels, and you can have different curves for each fuel, so you get kind of tighter tuning for both fuels. And then, but still, this is a pre-programmed curve, so you're still setting it and letting it run. It's not measuring anything, so you're not accounting for changes in ambient temperature. although you can have seasonal curves to account for that. So just switching from summer mode to winter mode to account for that change in ambient air qualities, but it does not account for changes in fuel quality either. Here's an example of a parallel positioning retrofit. So you see the motor has been replaced here. You got a Honeywell actuator on the air damper, and the other actuators are out of sight, but this is you don't always have to replace the entire burner. You can retrofit the burner, and we'll talk about that later. The next level of technology is parallel positioning with a VFD. So this is basically the same idea, but you're controlling the combustion air by controlling your combustion air fan motor speed with a VFD. So instead of dialing it back with a damper, you're turning down the speed of the motor and dialing the air back. If you're familiar with VFDs, this lends itself to electrical savings, and that's the benefit here. You also get tighter control. Dampers can also loosen over time, or seals can loosen, so the VFD should provide you with tighter control for longer, and then you get the electrical savings on the motor. The next level of technology is the full O2 trim. So here we're talking about getting all the parallel positioning benefits, but instead of operating exclusively from the pre-programmed curve, your actuators are going to be adjusted based on an O2 analyzer that's installed in the stack and the reading of that. So if you see on this control screen here, we are at, or they're operating at 2.1% O2. So that's really well tuned. Anything below 3 is pretty good. And then here they have the VFD on the blower motor. They're actually at full fire, so it's almost at 60 hertz. You see the reading, but as they go to partial loads, that'll turn down, and they're controlling their air that way. The boiler combustion is optimized, accounting for the entire firing range. Changes in ambient temperature, changes in fuel content is essentially equivalent to a continuous burner tuning. So it is just measuring the O2 in the stack and adjusting the ratios to get an ideal, I keep saying ideal, but an on point, I should say, combustion. Again, ideal is not actually attainable, but as ideal as you can be in the practical world. This system minimizes combustion air, maximizes efficiency, and reduces maintenance due to sooting, required tuning, etc. In some areas where burner tunings are required, this system can actually alleviate those requirements. So, or at least alleviate the frequency of the tuning requirements. I got a question here. What size boiler makes each type of control feasible? We'll talk about that in a minute. It's not a one size fits all kind of answer. A 200 horsepower boiler, you can get some savings that would pay back, and it's there's a lot of factors, but we'll go through some cost benefit numbers in a little bit, and then maybe that'll clarify what we're looking at. General note here. One major benefit, we touched on this before, but one major benefit of the advanced solutions is maintaining optimal efficiency across all firing ranges. So this increases your AFUE, which is annual fuel usage efficiency, which accounts for partial loading. So if you had a case where you have a boiler firing at full load all the time, you're not getting efficiency improvements from having these advanced controls. You could get your boiler tuned in to where it was it was burning at an optimal firing ratio, or fuel air ratio, getting optimal combustion, and you don't need all of this technology to get the same result. But in most cases, you're having some variation in your boiler load, and so you're going to get a lot of efficiency improvement on any modulating boilers with this with these retrofits. Any questions on this section? All right, we'll keep moving. Considerations for retrofitting. So when should you replace your burner? The obvious one is burner age. You start getting a burner that's 10 to 15 years old. It's maybe end of life anyway. So you're looking to replace it. And then you're concerned with, okay, what are the efficiency benefits here? We got another poll here, so please participate in that. Get some kind of feedback. The second consideration is the existing combustion technology. What do you have there now? You already have, a full O2 trim system, then, there's not really any benefit there. So, but if you're looking at the jack shaft linkage control, modulating burner, there's some improvement that can be had there, and it's can be significant. Do you have any new emissions requirements or carbon reduction goals? Again, it's kind of the same thing. Are you what are your goals? Are you looking to reduce costs? Or are you looking to reduce emissions? They kind of go hand in hand. So just how motivated are you to do that? Frequent maintenance issues. Again, that's going to be an indication that your burner is maybe needing a replacement. And then what is the condition of the boiler? If the boiler's struggling, a lot of tube failures, just kind of getting end of life, then maybe a complete boiler replacement is going to make sense. And then you get these efficiency benefits from the new technology that will come with the new boiler generally. So that might be your best option. Excuse me. If the boiler and the burner are in great shape, control retrofits may be the best option, like we saw that photo before, instead of a whole new burner. Safety concerns with poorly performing burners. So we mentioned flame rollout. So that's basically when the flame is not contained within the furnace and it's indicated by a discolored boiler jacket or streaks above the burner opening. Unstable combustion is a safety concern. You want a stable, reliable flame. Not something that's going to give you little poofs when you're starting up or when you're operating. Boiler sooting due to incomplete combustion is hazardous. Again, you're making hot spots in your boiler, which can lead to premature tube failures. It's very hazardous to clean. You generally are going to have a professional come in and do that. It's not recommended to try to do it yourself. If you think about it, soot is basically unburned fuel. And so it is flammable. And if you try to clean it yourself, you can create a hazardous condition. There's been instances of operators trying to clean their boiler themselves with a metal wire brush and creating a spark and the soot blowing up in their face. It's also an irritant to your skin. It's just nasty stuff. So it's just great to hire a professional to do that. And even better, it's great to have optimal combustion and avoid that situation in the first place. a lot of these efficiency opportunities come from operators wanting to avoid sooting, and so they turn their excess air up significantly to make sure that they're getting complete combustion, which works, but you're not operating as efficiently as you could be. Selecting the right burner. Burner type, you have gun type, wind box, integral head, etc. Capacity, generally you're going to match the existing firing rate of the existing burner. It's whatever is recommended. It was probably already sized correctly for the boiler. And so you're going to want to match that. Turn down ratio. So when you talk about turn down ratio, you're talking about the ratio of the maximum firing rate of the burner compared to the minimum firing rate that it can operate at continuously. So that's your turn down ratio. So if you can fire, if the max capacity is 10,000 MBH and the minimum continuously operating capacity of the burner is 1,000 MBH, then you have a turn down of 10 to 1. 10 to 1 is typical for industrial burners. 3 to 1 might be typical for more like commercial boilers or burners rather. And increasing the turn down leads to less cycling. So if you can have a lower firing rate, you can have less cycling, which is a big efficiency improvement. However, you can only turn the burner down so much before you start condensing in the stack. So just because you spec a burner that's capable of turning down 10 to 1 and you're replacing a burner that's 3 to 1, doesn't mean that in practice you can actually turn it down that far without causing problems. So that needs to be evaluated. And when the flue gas, when you do turn it down too far, basically what happens is boiler gets too efficient, your flue gas gets too cold, and it starts condensing in the stack. And then you get acids that are formed that will deteriorate your stack, and then that has to be replaced. So it's quite a problem. Anyway, other criteria: fuel type. You have natural gas, fuel oil, biogas, etc. The burner manufacturer is certainly going to want to know that. They will also want to know the available fuel pressure. That matters for sure. Furnace dimensions. So what are they firing into? Is it a fire tube boiler? Are they firing into that fire tube, or is it a water tube boiler where they have an open furnace inside? And then what are the dimensions on those? Are they in certain cases, they're trying to avoid flame impingement. If you're firing down a tube, then that fire's kind of rolling down that tube. But if you're firing into a furnace, they generally try to keep the fire off of the boiler walls so they don't get hot spots like that. So they want to know that. Boiler type. Really, you can just kind of give them the nameplate info on the boiler so they know what they're dealing with, which will also give them the furnace dimensions generally. And then what's the burner control system compatibility? Is that burner going to be able to plug and play nicely with the existing controls, or do you need control replacements as well? And then the emissions requirements, obviously need to know that so they know what they're trying to hit. And then what's the exhaust situation? How tall is the chimney? Is there an ID fan? What's the size of the ducting so they can have like an estimate of a pressure drop or back pressure on the flue gas. So those are all key criteria. Some other criteria to consider. What's the existing fan horsepower? And the consideration here for our purposes is what are the electrical savings we're going to get if we get a VFD saving, or if we get a VFD system. What's our new operating electricity going to be in comparison to the existing? Sometimes new burners will have a higher horsepower than older burners because they might have more pressure drop across the burner that the fan has to overcome. So you might even have a situation where you spec a burner with a VFD and it actually has higher horsepower, and so your electrical demand goes up. So that needs to be paid attention to. Is there service available? So the facility is going to want to deal with a reliable service company that's familiar with the burner model and manufacturer that you're specing, or that we're specing. And so that's generally important to them. Again, the higher technology you choose, hopefully the less maintenance is required, but you still have to have service technicians out from time to time. And you're still always going to have problems at some point. Is a new mounting plate required? So unless you're doing the same manufacturer and the mounting hole dimensions or mounting bolt dimensions are exactly the same, the burner throat and everything is the same, you're going to need a new mounting plate or some sort of modifications to the mounting hardware. What side of the boiler burner is the fuel train on? So this is something people don't think about, but Not accounting for it can result in awkward piping configurations to accommodate the new burner. And, the burner, and at times, or there's been cases of burners where they just have to install them upside down to get them connected right, which is not ideal. Maybe acceptable for certain burners, but it's something to note for sure. Is there any intake ducting? Need to account for the inlet pressure drop, as well as the that matters for ambient air temperature. So if you're pulling air from the room, your temperature is going to be a little more consistent. If you're pulling it from outside, you're going to have bigger swings in combustion air temperature. And then finally, are there any noise requirements? So a typical requirement is 85 or below 85 decibels at 3 feet. Combustion air fans can easily exceed that, and so sometimes require an inlet silencer. So that's another thing to consider. So what's their best technology? And we kind of touched on this earlier with that question from Amir, but single stage, basically, we're saying that's out. Multi-stage, it's only going to make sense for very consistent loads, very low run hours. Modulating is basically dated. I think most commercial burners are going to have parallel positioning now at a minimum, unless there's just some reason to really, try to go cost effective on the initial purchase. So basically, we're saying more is more here. Do you want parallel position or do you want the full O2 trim system? That's going to be a function of cost and return on investment, as well as maintenance considerations and extending the life of your boiler, which you're going to get the most life out of your boiler with this full O2 trim system, assuming everything's functioning properly. Any questions there? Okay. Now we'll talk about utility incentives. Incentives vary by utility and even between service areas of the same utility. They can be complicated to navigate, but represent a significant financial tool to increase the savings attained through retrofit projects, which increases your return on investment, right? Oh, we got another poll here. So yeah, please participate in that. Steam management can provide the engineering studies required, design, procurement, installation, commissioning of turnkey projects, and guidance on the incentives, as well as administration services for incentives. But basically, the incentives available are going to be whatever incentives available for these types of measures for an engineering study. That's a common thing where you get a pre-approved proposal to the utility. They will approve an incentive amount for a study to evaluate these retrofits. It seems to be common for that to be maybe half of the study, depending on the price of the study. It'll have some sort of cap. And then the burner upgrades themselves are usually going to be eligible for a therm savings, like a custom rebate based on therm savings. So $2 to $6 per therm is a reasonable figure. And usually the utility incentives engineering team is going to give you some guidance on how much savings they're going to give you credit for. So you can have all the best calculations in the world and say you're going to save so much money. And like, for example, you could reasonably calculate that you're going to save 7% on this retrofit, and that really is a realistic number, but the utility will only give you credit, may only give you credit for 2 to 3% savings. So it's you definitely want to consult with them, which we do, and kind of get all that laid out so we don't get surprised and kind of inflate our savings numbers to the client, or incentive numbers rather. I got a comment here. Illinois is $1 per therm for custom. Okay, interesting. I know National Grid is like $2 to $3 per therm. There's some utilities out west that are higher. So yeah, it's all kind of on a case by case basis. Cost benefit analysis. So these are annual boiler costs. So you see all the different categories there, but the main takeaway here is that your fuel is about 45% of your annual cost. And I actually saw a rule of thumb that your fuel cost can equal 4 times the initial cost of the boiler, which is really high. But yeah, it's a significant cost. So we'll look at that next. So here's an annual cost example. So estimate the annual fuel spend for a 200 horsepower boiler. Fuel expense equals boiler horsepower converted to 1,000,000 BTUs divided by your boiler efficiency, which gives your firing rate, times your average load, times your fuel cost, times your operating hours. So for 200 horsepower boiler, you get the 200 there divided by 80% efficiency is a pretty conservative number for fire tube boiler. 65% loading. This is a heating application. So we're talking about 5,100 hours per year, $9 per 1,000,000 BTU. There's about 10 therms per 1,000,000 BTU. So we're talking about 90 cents per therm, which is a pretty typical cost, maybe for like New England. So you have a fuel expense of $250,000. So if you're talking about improvements resulting in 5 to 7% efficiency improvements, you're talking about $12,500 to $17,500 per year in savings. And then tack on to that your available incentives and reduced maintenance costs, and you can get a pretty reasonable payback on these retrofits. I would say not just reasonable, but appealing. So here's a cost benefit analysis. So we have a combustion optimization example. So for this example, a natural gas boiler is operating with jack shaft combustion control under the following conditions. We have a 300 horsepower boiler. You see the steam flow at the bottom of the table there, 10,000 pounds per hour. That's about a 300 horsepower boiler. Another takeaway here is that it's at 79% efficiency, 11.5% O2. So that's kind of the initial setup there. We're operating at 8,000 hours per year. This is a manufacturing application. This is actually a real application from an adhesive factory. So this is real process data that we evaluated. And they have a pretty low fuel cost here, $7 per 1,000 SCF, but that's about $6.40 per 1,000,000 BTU. And again, you think about that 11% O2. Back to this chart that we were looking at, the highest efficiency operating region, they're saying 1 to 2%. 1% is pretty low. You're going to start getting some sooting there, which actually indicate here because this hydrocarbons is your soot, basically. So you really want to be more like 2%, even finely tuned in. But the point is 11.5% is way out here. We're way too high with that. So the solution one is your traditional solution, which is a combustion tuning, your serviceable maintenance. A boiler technician comes in, tunes your boiler, or your burner rather, and it's reasonable to achieve an average of 6% O2 across the firing ranges, and as well as between, accounting for the fact that it's going to get out of tune before your next tuning. So you have the technician come in, tune the burner, get down to 3, 4, 5% O2 across the firing ranges, and then it slips out. And so on average, it's 6%. Your savings about $30,000 per year. You got some incentive there, possibly, depending what area you're in. And the project costed $2,500. So keep that in mind. We'll look at the we're going to look at the cash flows for these solutions in just a minute, and you'll kind of see the difference. Some notes here. It does not necessarily cover all operating ranges, does not account for changes in ambient temperature, does not account for changes in fuel quality, may easily get out of tune and may need to be done periodically. And tuning is recommended twice a year for heating only applications and 4 times a year for year-round application. Solution 2, we have an O2 trim retrofit. So not a burner replacement, but a retrofit. It's reasonable to achieve an average of 2.5% O2. I'm saying 3% in my calc, but you can really get this thing dialed in with an O2 trim, and it stays that way, assuming the system's operating without any issues, which it should. So you're getting an annual savings of $38,000 for a project cost of $50,000, incentives of $25,000. So that's on a therm basis, and basically we're assuming that they have a cap that's 50% of the project cost, and it's getting maxed out. Because if you say $2 a therm, then you're close to $120,000 for I don't know if that's right. I just said it off the top of my head, but it's maxed out is the point. So notes here, covers all operating points, does account for changes in ambient temperature, does account for changes in fuel quality, equivalent to a continuous tuning, and your combustion fan motor electrical savings can be significant from VFD operation. And we actually don't have the motor savings in, so that we're just talking about fuel savings here. So here's the 10-year cash flows on that. So we have option 1 is your combustion tuning. So your initial outlay is at $2,500 minus the incentive, $750. Option 2 is your project cost minus incentive, $25,000. This is an O2 trim system retrofit. And then option 3 is a completely new burner. We didn't put that in the solutions, but it's the same savings calculation as the O2 trim retrofit. So we're talking about a completely new burner with O2 trim. We're saying that's a $100,000 project with some incentive, so you're down to $25,000 for the project cost, or $75,000. Sorry. So you see your cash flows here are your savings, your fuel savings. For option 1, though, the reason it's lower than the other 2 columns, well, for one, you weren't getting quite as much savings, but the other thing is you have a repeatable expense for that service technician to come out. So it's eating into your savings here. You're having them out. This is a year-round application, so we're saying in order to maintain these savings, you're going to have them come out 4 times a year. And so that's eating into your savings here. Option 2, you're realizing the full benefit of the savings. Same for option 3. Those are escalated 3% year over year. But then all these savings numbers are discounted back based on a 12% cost of equity to give you your net present values of the projects here. So this is a good way to evaluate the viability of projects financially is net present value. So you see your first course of action is significantly less net present value than your O2 trim system. And then even your new burner is still better than continuing to tune an existing linkage burner, even assuming that burner has 10 years of life left in it without needing replacement anyway. So that's kind of the just a generic example with specific process data, but it gives you an idea of the type of savings you can achieve here. And that is it. Any questions? We're going to hang on here for a little bit. I do want to thank everybody for attending, but we'll hold up here and kind of make some announcements before we log off and allow everybody to get their questions in.